Hello everyone, welcome to my first tutorial screencast of game development with C++11. We are gonna build an Arkanoid or Breakout clone using the latest standard of C++ and the SFML library. So I'll begin by showing you the end result. This is what we're going to build. It is a simple game with collisions between the ball, the paddle and the bricks. It's very simple, and the code is only 160 lines long, with new lines and comments, so it's very short. Before I begin, I wanted to say that the intended audience for this tutorial is someone who has a little programming experience, especially if it is C++ experience, and also a basic idea of how a game works. I'll be using GNU Linux, Arch Linux as my operating system, Sublime Text as my text editor, and Clang++ as my compiler. The important thing is to use the std C++11 command line parameter when you compile, so that we'll be able to use the new features of the standard. I've divided the code in 9 segments, and we're going to analyze every single segment and show the result of that specific segment. So let's begin. This is the first part of the game. It is only 30 line long, and it basically only displays a window on the screen. We need to include SFML libraries, headers, we need window and graphic headers. We'll also be adding the using namespace directives in the code that basically allow us to stop repeating std : and sf : from every single in every single line we use those features. And we are going to find some compile time values, which are constants, using the new C++11 const per word, which basically forces the constants to be computed at compile time, and that way we'll be sure that they cannot be modified during the execution of the program, and that we will get maximum efficiency. So we're gonna create a constant for the width of the window, which is 800, and a constant for the height of the window, which is 600, of type int, integer. We are gonna also have our main program entry point, which is the usual int main function with no arguments, and we are gonna create the game window using SFML. SFML is a very nice library. It's free and open source, and it makes dealing with graphics, input, and windows very easy. The class we are gonna use is a render window, which is obviously from the SFML library. And we're gonna instantiate the window with these parameters. As you can see, we're also using the new C++11 initialization syntax, where we use curly braces to initialize an instance of render window, and it's the most safe way of initializing values, as it prevents mistakes about conversions. So if, for example, I initialize an int like this, in the first case I will not get any error. Maybe I will get a warning because there is an implicit conversion from double to int here. In the second case, I will most likely get an error because this is an implicit conversion which loses information, and the curly brace initialization syntax prevents this conversion from happening. So we create our window by having a pair of integers that are the width of the window and the height of the window, and also a title, which will be Arkanoid 1. We will also need to set a frame rate limit for this game, because we are going to use fixed frame rate for simplicity. So we're gonna set our frame rate limited to 60, as most games do. Game development works around the idea of having a single big game loop where we at the beginning of the game loop, we clear the window from the previously drawn graphics. We check input and update our game entities in the middle of the loop, and then we display the new contents of the window. In the middle of the loop, in this demo, we only have the input condition that checks if the user pressed escape on the keyboard, and if he did, we break out of the loop, practically ending the program. So let's see how this demo works. As you can see, it's a black empty window. Nothing really happens, but if we press ESC, we can get out of the program thanks to this condition. Keyboard is a global object that SFML gives us so that we can check the status of the input. There is also a mouse object and a joystick object that work pretty much in the same way. So let's go to the second code segment when we finally add the first element, which is the ball. So the first change is adding another constant here, const per float, which is the radius of the ball. We are going to set it to 10. And we also need to create a class for our ball. I'm using the struct keyword, which is basically the same as class in C++, but everything inside the struct is implicitly public, and that's what we want for this segment, as it's going to make it a lot more simple. So we create this new class ball, and as a member of this class, we add a circle shape, which is an SFML class that defines a circle that can be drawn, moved, and we can set its color, its origin, and so on. It's a very handy class, and it's basically going to handle the rendering and the position for us. So we instantiate a member inside ball called shape, which is of type circle shape. We'll also need a constructor that takes two arguments, mx, which is the starting x coordinate of the ball, and my, which is the starting y coordinate of the ball. This is how you define a constructor in C++. You say the name of the class, open parentheses, the parameters you want the user to give, and inside the curly braces you do some instructions that will happen at construction time for the ball instance. So inside the constructor we apply the position to the SFML shape, the radius to the shape. We set a color, in this case I chose red, and an origin for the shape. We want the origin to be the center of the shape, so our origin will be two coordinates, x and y, equal to the ball's radius, so that the origin will be precisely in the center of the ball. Now in our main function, we need to create an instance of ball, and we'll position it at the center of the window. So again, we create a variable of name ball, of type ball, and we initialize it using the uniform curly brace syntax from C++11 with the width of the window halved and half the height of the window, so that the ball will be in the center of the window. The rest of the code is identical. The only new thing is inside the game loop, after we get the input, we need to render the ball instance on the window so that it will be visible to the player. And this is done by using the draw method of the render window, which takes any drawable object. In this case, circle shape is a drawable object, and we can directly pass it in the draw function of the window. Let's see what it looks like. As you can see, we have a static ball in the middle of a window of red color, and nothing else for now. Let's move on to the next segment. This is the third segment, and here we define a new constant, ball velocity, that is a constructor float, and it is set to 8 because it's a nice value by trial and error for the speed of the ball. We also create a new member of the struct ball, which is velocity. Velocity is a vector to f, which is an SFML type that stores two floats. It's a mathematical vector that you probably studied in your physics class. and we initialize it with the curly brace initialization syntax with minus ball velocity and minus ball velocity. This means that the velocity of the ball is a negative vector, and it will move towards the top and the left of the screen. We also need to update the ball every game loop iteration by moving its shape by the velocity. This is the most common way of dealing with movement in game development, and probably it's the best one. Basically, every game loop iteration you change the position of the object by a certain velocity to give the illusion of movement. And after we define this method update, we need to call it every loop iteration, so we just put it inside the while. Let's see how it looks like. As you can see, the ball moves towards the top and the left, but it goes outside the window. We need to prevent that somehow. So, to prevent that, we will move to the fourth segment of code, and we make some changes in the update method. Before I get to the update method, I also created some common property methods to easily get the left, right, top and bottom side of the ball. And they work in a very simple way. Basically, since we know that the X and Y position of the ball is the center of the ball, by subtracting the radius from the center X coordinate, we get the left coordinate. By adding the radius to the center X coordinate, we get the right coordinate. And the same idea can be applied to top and bottom. So, we need to find a way to keep the ball inside the screen somehow. The best way to do this, and the most common in my opinion, is checking if the position of the ball is outside the window, and if it is, we change its velocity so that it will change the direction of movement in the following frames. So we can check if the ball is leaning towards the left by checking if the left side of the ball is less than 0, as coordinates in SFML start at the top left corner of the window with 0, 0, and finish at the bottom right corner of the window with the width and the height of the window. So if the ball is leaning to the left, if left is lesser than 0, we set the velocity, the x velocity, to a positive value so that the ball will move towards the right, preventing the ball from leaving to the left. Otherwise, if the ball is leaning towards the right, we need to set the horizontal velocity to a negative value so that the ball will move towards the left. So, else if the right coordinate is bigger than the width of the window, the x velocity will be set to a negative value, so that the ball will move towards the left in the following frames. The exact same idea can be applied for top and bottom collisions, using the y velocity instead of the x velocity and the height instead of the width. So let's see what it looks like. As you can see, we have a ball moving in our window. If it's leaning towards the left, its velocity will become positive, so it will move towards the right. If it's leaning towards the right, its velocity will become negative, so it will move towards the left. And the same can be said for the top and the bottom coordinates. Let's move on to the next code segment. So, we will now add a pedal in the game, which is basically the player. We'll create some constants first, the width, the height, and the velocity. Just like the ball and the window, we need some values to use throughout our code. And here, similar to the ball class, we create a paddle class with the keyword struct to make every member public. Instead of using a circle shape, we use a rectangle shape, as we want our player to look like a rectangle. And we also have a velocity vector, just like for the ball. We also need a constructor, again similar to the ball, that takes the x and y starting position. And inside the constructor, we also need to set the size of the rectangle, which will be a vector, initialized via the C++11 initialization syntax, which is basically the same as doing this. these two lines of code are equivalent. And we initialize the size of the shape with the width of the paddle and the height of the paddle. We give it the red color, and the origin will be the center of the paddle. And we can get the center by simply dividing the width and the height by 2. We'll also have an update method for the paddle. As you can see, we're following a very simple pattern where every entity in our game will need to be updated and drawn in the game loop. And we need to move the paddle by getting the keyboard input and changing its velocity. So this might look complex, but it's very simple. We also need to keep the paddle inside the window, so we will change the velocity of the paddle only if its position is inside the window. So if the player is pressing the left arrow key and the left side of the paddle is greater than 0, we will move the paddle to the left by setting its x velocity to a negative value. Else, if the player is pressing the right arrow key and the right of the paddle is less than the width of the window, and by that I mean if the paddle is inside the window, then we'll move the paddle by a positive value in the x velocity, and that will make the paddle move towards the right. Else, if the player isn't pressing anything, we need to stop moving the paddle, and we can do that by setting the x velocity to 0. We also need to create a paddle instance in our main function, like we did for the ball, and we set its position to the center of the x coordinates of the window, and 50 pixels higher than the bottom side of the window. Inside the game loop, as we did with the ball, we also need to update our paddle and draw its shape on the window. So let's see what it looks like. Here we have our paddle. We can move it left and right, and it will not go out of bounds. There is no collision between the paddle and the ball yet, but we'll get there in the next code segment. Okay, let's deal with the collision between the paddle and the ball. So to do that, we need to use a new function. It is a generic function to check if two shapes are intersecting, and by intersecting I mean colliding or overlapping. This is a C++ feature. It is a template which allows us to create compile time variants of a single function for different types, so that we can easily use this function to check for collision between rectangles, circles, and any shape. And we create this template function called isIntersecting that returns a Boolean value and takes two references as parameters to two generic objects. To check if two objects are intersecting, we will simply check if the right side of the first object is inside the left side of the second object. So if the right coordinate of the first object is greater or equal than the left coordinate of the second object, and the left coordinate of the first object is less or equal than the right coordinate of the second object, we know that there is an horizontal intersection. If there is an horizontal intersection and there is a vertical intersection, which is basically the same as the horizontal intersection but with bottom and top instead of right and left, we can safely say that the shapes are intersecting. To visualize this collision detection a little more easily, this is a slide I created for the Linux Day in my city, where I had a talk about this game and its creation. And as you can see, these two are our objects, and this is the horizontal intersection that we get by subtracting the left of the second object from the right of the first object, and this is the vertical intersection. And if the right side of the first object is greater than the left side of the second object, and the top side is less than the bottom side, you can see that the two objects are intersecting. So that's basically how it works. It might seem complex at first, but if you sketch it out and see and visualize graphically what's happening, it's very easy to understand. So we also need a function to deal with the paddle and the ball collision that will call every iteration of the game loop, and it will allow us to respond to this collision. So as you can see, we call test collision every loop iteration using the paddle and the ball as arguments. In fact, test collision takes a reference to a paddle and a reference to a ball as its arguments. If there is no intersection, and by that I mean if the paddle and the ball are not colliding, we simply get out of the function, we return, because there is no response to take. Otherwise, we need to push the ball upwards by setting its velocity to a negative value, so that it will bounce off the paddle. Another important thing is to direction the ball dependently on the position where the paddle was hit. So if we hit the paddle on the left side, we need to push the ball towards the left. Else, if we hit the paddle on the right side, we need to push the ball towards the right. This is done by simply checking the x-coordinate of the ball and the paddle, which is the center x-coordinate. And if the x of the ball is less than the x of the paddle, we can safely assume that the ball hit the paddle on the left side, and we can move it to the left. Otherwise, we'll just move it to the right. And here is what it looks like. As you can see, the ball bounces off the paddle. If we hit the right side, it will go on the right, as you can see here. If we hit the left side, it will go on the left as soon as I have a chance. Yeah. Let's move on the seventh segment of this code, which is the segment when we create the bricks. So we'll start by defining some constants, the brick width, the brick height, and the number of bricks on the x coordinate and the number of bricks on the y coordinate. So basically we will have 11 multiplied by 4 bricks at the beginning of the game, which equals to 44. We'll also create a brick class very similar to the paddle class that has a shape, which is a rectangle shape, and also a boolean member called destroyed, which will allow us to check and set whether a brick has been hit or not by the ball. The constructor is almost identical to the paddle constructor, as you can see. It takes the starting x and y position. The only difference is it uses the brick constants, and it is of yellow color. So now we have a problem. We need to have 44 instances of bricks. We could either write 44 variables by hand, but that is obviously an horrible solution, or we could use a standardized container, std vector, that will allow us to contain any number of brick instances and easily iterate over them to perform game logic. Vector is a standard template class, so we need to specify what kind of item it will contain by specifying a type between angular parentheses, as you can see here. So basically bricks is a vector containing brick instances. We also need to fill up our vector in a grid-like pattern to create a wall of bricks using a bidimensional for loop. We will have an x index and a y index. The x index will range from 0 to the number of columns, and the y index will range from 0 to the number of rows. So if we nest these two for loops, we will get 44 iteration, which is the number of the blocks. And for every iteration, we will emplace a block directly inside the bricks vector. Emplacing is a new C++11 mechanic that allows us to directly construct an object inside of a container, allowing better efficiency and more intuitive code. EmplaceBack is a templatized function that exactly takes the same parameters as the constructor of the type held by the vector. So our brick constructor takes two parameters, which are the x and y coordinates, and EmplaceBack therefore will take the x coordinate and the y coordinate of the brick. We will multiply the width of the brick by a specific offset by the index of the loop, so that every brick will be next to each other with a small offset in a wall-like pattern, a grid-like pattern. We'll also need to draw every single brick on the window. We do that by using a C++11 for each loop that allows us to intuitively say, draw every brick in bricks. This line of code is equivalent to a traditional for loop like this one. But this new for each loop is much more elegant in my opinion, and also can be more efficient. So it basically says, for autoref brick, so for every reference to brick inside of bricks, draw the brick's shape. Auto is another C++11 keyword that automatically infers the type of the variable. So basically, if we had the brick ref here, it will be the same exact code. And by that I mean that these two lines of code are perfectly equivalent. Auto is just a way to allow the compiler to automatically deduce the type of the variable without any kind of performance hit. We also need to use ref, as we don't want to create a copy of every brick during the iteration. We want to draw that exact brick contained inside the vector. So basically we are using this line to say, draw every brick in bricks. Let's see how it looks like. Perfect. We have our bricks in a grid-like pattern, and every single brick is getting drawn every loop iteration, as you can see here. Let's move on to the collision between the ball and the bricks. Let's move on to the final and most difficult part of our little Arkanoid clone, which is the collision detection and response between the ball and the bricks. So the classes are exactly the same. The new thing is this new function, taskCollision, that as the older one that took a paddle ref and a ball ref, takes two arguments, but in this case we have a brick ref and a ball ref. So we are going to test collision between a single brick and the ball. If there is no intersection, we get out of the function, as we did with the paddle and the ball, by simply calling return. Otherwise, if there is an intersection, the brick has been hit. So we set the brick dot destroyed, which was a boolean value here inside of brick, to true, to basically say that this brick has been hit by the ball. Now what we're gonna do is very complex, because we need to create a realistic response for the ball bounce, and to do that we need to see what side of the brick has been hit by the ball. To do that we need to calculate how much the ball overlapped the brick in every direction, and we can do that by simply using some subtractions. To see how much the ball has overlapped the brick from the left, we create a new variable, overlapped left, and we subtract the right side of the ball from the left side of the brick, so that we will get the difference, and by difference I mean the magnitude of the overlap on the left side. We do the same for the right, the top, and the bottom side. Now we will probably have if in the case, for example, of a collision from the left side, a very small overlap left and a very big overlap right, because the subtraction gives us the difference in coordinates, and if the ball hit the brick from the left, the difference between the right coordinate of the ball and the left coordinate of the brick will be very small. The same idea can be applied for every direction. So now we need to understand if the ball came from the left or came from the top side. To do that, we apply the idea I just explained. If the magnitude, and by magnitude I mean the absolute value of the overlap left, is less than the absolute value of the overlap right, the smallest overlap is overlap left. So ball from left will be set to true. Otherwise, if the overlap right is smaller than the overlap left, the smaller value is overlap right, and bar for left will be set to false. We will apply the same idea for top-bottom collisions. If the overlap from the top is smaller than the overlap from the bottom, the ball hit the brick from the top. Otherwise, the ball didn't hit the brick from the top. We also need to store the minimum overlaps for the x and y axis, and to do that we simply use a conditional operator here that stores a value inside of these float variables. So the minimum overlap x is overlap left if the ball hit the brick from the left. Otherwise, it is overlap right. The minimum overlap value on the y-axis is overlap top if the ball hit the brick from the top. Otherwise, it's overlap bottom. So, if the magnitude of the x overlap is less than the magnitude of the y overlap, we can safely assume that the ball hit the brick horizontally. Otherwise, we can safely assume that the ball hit the brick vertically. Therefore, upon our assumption, we can either change the x or y velocity of the ball, creating a realistic response for the collision, basically by giving the ball the right direction for the bounce. So, if the ball hit the brick horizontally, we will set the x velocity to minus ball velocity, so to a value that makes the ball move to the left if the ball hit the brick from the left. Otherwise, we will set to a positive value, so the ball will move to the right. Else, if the vertical overlap was smaller than the horizontal overlap, we will work with the y velocity. And if the ball hit the brick from the top, we will make the ball go upwards. Otherwise, we will make the ball go downwards. This is very complex, but if you pause the video and take a look at the code, you should be able to understand what's going on. We also need, in the main loop, to check this collision between every single brick in bricks and the ball, and we'll do that by using another C++11 modern for each loop. For autoref brick in bricks, we check the collision between that brick and the ball. So basically this will run 44 times if all bricks are alive. And if you remember, if there is a collision, we set the brick destroyed to true. So we need a way to remove the destroyed bricks from the bricks vector. To do that, we use an STL algorithm that removes all the destroyed blocks from the block vector using a cool C++11 lambda. So this is a very interesting line of code. It may look complex, but if we analyze it, we can understand what's going on. So, the bricks.arrays method takes a start iterator and end iterators parameters, and basically it deletes every object, every item between the start and the end iterator from the bricks vector. Now we need to sort the bricks so that the end of the vector will contain all the destroyed bricks and the beginning of the vector will contain all the alive bricks. To do that, we use removeIf. removeIf is a STL algorithm that takes a range, in this case the entire bricks vector, and a predicate. A predicate can be a function or a lambda, as you can see here, that basically says remove all bricks from the brick vector if the brick has been destroyed. removeIf doesn't actually erase any item from the vector, but instead sorts the items that satisfy the predicate and puts them at the end of the vector. removeIf actually returns an iterator. So we use removeIf as our start iterator in the erase method. So basically this line is telling the compiler to remove the range starting from the first destroyed brick to the last destroyed brick from the bricks vector. And that will effectively remove all the destroyed vectors, all the destroyed bricks from the bricks vector. It is not very simple to understand at first, but it is a very effective and efficient way to remove all the bricks from the vector, as the removeIf algorithm is very efficient, and we erase a range with a single instruction, so that the vector will not get modified multiple times if multiple bricks are destroyed. So let's see what it looks like. Perfect. Now we have a fully functioning Arkanoid game written in modern C++11 with collisions and very simple graphics, and it's about 160 lines of code by moving around some methods and removing the comments. So, thank you for watching. I will upload the code on my website so that you will be able to download it and play around with it. As this is my first screencast tutorial, I greatly appreciate any comment, suggestion or criticism, so that my next tutorials will be easier to understand or more interesting. You can directly contact me on the video by posting a comment, or if you want you can visit my website where I have many social network links from which you can reach me, or simply send me an email. Thank you for your attention. Hope you enjoyed the tutorial.